Hi, I'm Nikki.
And I'm Dennis, and we have designed the Air and Space Thermal Rocket Engine known as ASTRET. We didn't build it, but we have built a spaceplane simulator in order to show its capabilities. We have designed this engine in MATLAB, Solidworks, and we have built it in Kerbal Space Program, which we will demonstrate inside our simulator. As you walk in, you are seeing all of our control surfaces and the screen on which the simulation will run. So, this is our joystick, Nikki's joystick. This is our throttle for controlling the thrust of the engines. Here we have all of the controls for the spaceplane itself. This is our computer controller, keyboard, mouse. Nikki?
These are our seats where you can control how comfortable you want to be during flight. And then this is our LED panel where you can control the LED lights that are around our simulator.
And we are about ready for takeoff, so wish us luck. Alright, we're inside the space plane. How are you feeling, Nikki?
Great. It's beautiful in here. Very spacious.
Alright. You ready?
Let's go.
You gotta start the engines. You gotta press that big button. Go ahead and increase the throttle. Yep. All the way. And pull back on your stick.
To 20.
220, yes. Alright. You're at 20. Okay, go ahead and hold that. I'm going to go ahead and set the autopilot to 18 degrees. Alright, just keep holding that. Okay. We are in autopilot right now. We're going to go to 15 kilometers. And then we're going to drop down our pitch to about 10 degrees. So at this point, we are not using any propellant. We're just using the atmospheric air and the power of fission to heat it up in order to produce the thrust. We are at 10 kilometers in altitude, and we can see how our thrust is starting to drop because the air pressure is starting to go down too. Our speed is above Mach 2. Alright, Nikki, I'm about to take off the autopilot.
Go down to 15.
Go down to 10.
Go down to 10.
Easy does it. Alright, that's good. Hold it there. Autopilot engaged. Alright, so now we're going to keep this pitch up until about 25 kilometers when we're going to run out of usable atmospheric air, and we're going to need to engage the rocket engines. So when that happens, go ahead and flip the SW2 switch down, and that'll get your rocket engines going. And then what we're going to do is I'm going to slowly decrease that throttle in order for us not to release too much radiation into the environment. So we're still going to be using a lot of the air, and as we're flying through here, I'm going to slowly increase as our altitude increases, just like in our simulations.
So is this a point where we can understand that radiation from our engines is not a concern because we're so high?
Yes, exactly. So at around 50 kilometers in altitude, we're going to be at full throttle, all propellant, no air, but at that point space radiation becomes prevalent, and it doesn't matter what we're releasing at that point. And whatever we are releasing is still already in the environment, and those particles like hydrogen and krypton already irradiated by space radiation. Alright, Nikki, let's go ahead and switch on the rocket propellant. Around 25 kilometers. Alright, at 30 kilometers we're going to increase our attitude, and we're going to be using our RCS thrusters because we do not have much air left.
What are we increasing to?
15 degrees.
Alright.
Increasing the thrust to about 5 meganewtons. Right. Go ahead and switch to 20 degrees. At 40 kilometers, we're going to increase to 6 meganewtons. We're going to go up to 25 degrees. We're going to go ahead and switch to full rocket propellant. Go. Increase to about 35 degrees attitude. Stabilize a little bit. We're trying to increase our time to Earth opiapsis, and as this time progressively increases, we're going to decrease our attitude. That way we can deliver more force to the horizontal direction, as we will be high enough in our orbit. Alright, we're going to back off the throttle a little bit and level off at around 400 kilometers in altitude, which is the altitude of the ISS, stands for International Space Station. Alright, that's good. Now we're going to go ahead and warp to about the opiapsis in order to circularize our orbit. As we can see, our periapsis is at only 85 kilometers in altitude. We want to get that up to about 400 as well. Alright, so now we're just going to stabilize and increase our thrust. Get the periapsis up to about 400. Now, as you can see, our thrust doesn't go down immediately as we cut off the throttle. That is because the reactor is relocating some of that propellant/moderator through to the wing turbine in order to keep itself cool enough that way we don't have a meltdown. That's why we still have some of that lingering thrust going. Alright, so now we are going to go to the day side, that way we can see better and release our payload. Right around Baja, Mexico would be pretty good, right? Or I'm sorry, Baja, California would be pretty good to release, right?
Yeah. And then we'll be set up to re-enter.
Then we'll set up to re-enter. Exactly. But right now, our payload will remain in this orbit, and it will not be able to get out of this orbit because it does not have any rocket thrusters. So it's just going to stay there for probably from 10 to 20 years before orbital degradation sets in and it starts falling down slowly to the Earth.
So how are you going to navigate the payload
out of the space plane?
Yes.
Through the use of RCS thrusters.
Okay.
Alright, Nikki, go ahead and open the cargo bay doors. That's SW3. Up.
Alright, opening the cargo bay doors.
Alright, now we're going to release the cargo. Go ahead and press SW5.
Releasing cargo.
Alright, switching to cargo. Control. Alright, engaging. Oops.
is just the nitrogen, as you said.
Yes.
Thrusting
Yes.
the payload forward or away from the plane.
Exactly. That way we can safely close our cargo bay doors and keep on our way. So now we're going to get our payload set up with the solar panels engaged. Alright, now that our solar panels have been extended, we also want to open up our docking bay. That way the next space plane or the next item that will be docking, which could possibly be another fuel tank, could be docked to it. This in particular is a fuel tank for a future mission, possibly to Mars or to the moon, that the space plane will dock to, get its fuel, and continue on board.
So it doesn't necessarily have to go to the ISS.
It does not necessarily have to go to the ISS. It could, but it doesn't need to, as it does have automatic control. Here, this is our pilot, right? There, yeah. So we can make it into hibernation mode. It's got reaction control, so it's pretty much just like an onboard pilot, just a computer.
Okay.
So we're gonna go ahead and go back to the space plane. Nikki, SW3 to close our cargo bays.
Closing the cargo bays.
Alright. And now we have lost significant mass because that was 70 tons of payload right there. 70 tons is comparable to that of the SLS system, or space launch system that NASA is designing right now. And that system costs about $500 million to launch for one single launch. This space plane, after the initial building costs of about $1 billion, and the reactor changeouts every 140 flights, over the life of about 1,000 flights, it would accumulate to only $8 million per launch. That is a significant difference, and the strength of this space plane is that it is reusable. Its best competitor is actually Elon Musk's BFR, or Big Falcon rocket. That one's got a price of $20 to $40 million per launch. So we are still, our space plane is still winning on that. Alright, so now we will go ahead and engage in orbital reentry maneuvers, but first we need to see exactly where we want to reenter. Now, if we decrease our thrust now, our periapsis is going to decrease there, so we're only going to reenter around here, which is probably going to be around Australia.
We don't want to.
We don't want to really land in Australia. We kind of want to come back to the United States, to Florida specifically. So what we got to do is go to our periapsis right around this point, and this is where we want to decrease our opiapsis, which is going to be our periapsis once we start decreasing. And we'll go ahead and try to land in Florida. So let's go ahead and warp here. Alright, so we're going to go in our retrograde direction. So retrograde means we're going against our orbital direction. Prograde means we're going with it. So retrograde means that we're actually going to decelerate. So before we decelerate, we just want to see what our periapsis and opiapsis values are. So now we're going to slowly increase our thrust, and we're going to bring down our periapsis to about 50 kilometers. The advantage of this spaceplane is that it's not very sensitive to the altitude that we descend at. So for example, right now we're descended actually to 40 kilometers. That's fine because we do have our wings, and our wings will actually help us get back on track. So what we're going to do is we're going to increase our angle of attack to about 30 degrees right now.
And as you descend into the atmosphere, you can just manipulate the way the pitch is to accommodate for whatever scenarios you could possibly come up with during the descent, correct?
Exactly. It has an advantage over the space shuttle. It is not locked into one place or one region where it can land. It can actually go ahead and go around the world because of its huge wingspan.
Because at the end of the day, it is a plane, nonetheless.
It is a plane, exactly. So we just brought down our angle of attack a little bit lower. So as the atmosphere becomes thicker, we want to keep that angle of attack smaller and smaller. That way we don't induce stall. Now stall is where the flow separation occurs at the wings. So the spaceplane has no more lift and it loses control. As you can tell, we do have these heat bars coming up, and that is because the friction of the air is heating up our control surfaces. Now these white things that are sticking out, these are aero brakes, so we're just trying to control them in order to control our descent and in order for us to slow down even more. We are still going at 7.2 kilometers per second.
So at this altitude, it's still okay that we're going this fast, and noise is not a concern, especially because we are over the ocean. So there isn't anybody down below trying to sleep or anything in houses, so it wouldn't disturb.
And we will be going supersonic above the ground, but we will be going at such an altitude of around 15 to 20 kilometers that is just so high that any noise would not affect whoever is living down there.
So why is it that we are going up, and we were just at 88 and now we're at 91 kilometers?
That is because we kind of bounce. So when you throw a rock in the river and it kind of bounces, that's what's happening here, is that we're going so fast and our surface area is so large that we actually bounced off the atmosphere. And we can actually use this effect, one, to slow down, and two, to keep our altitude and possibly even orbit if we have enough propellant to get back to orbit. For example, a military mission where it needs to drop off some payload, it will be able to do that, change its orbit, release its payload, and then regain its orbit while the payload continues on its trajectory.
So at this point, when we're lower in the atmosphere, we can see a little glowing red at the...
That's a warning that our part, as an aero brake, is getting a little bit too hot. So right there is getting a little bit too hot, but that's okay. As long as we don't overstress it, it'll be fine.
And then you're adjusting the pitch
because the pitch was too high and we were going so fast. We're actually creating some lift because we are in the atmosphere right now, in the upper atmosphere, but we are still in the atmosphere. So I'm trying to eliminate that pitch, that way we can go down further into the atmosphere and use the air in order to slow down even further. Gonna back off the aero brakes. Nikki, can you please switch us to atmospheric propellant, please, by switching SW2 down? Perfect. Alright.
And now this is just using the air.
Yes, this is using the air as the propellant. Right now we are just heading to Florida. We have slowed down quite a bit. Now we are just gliding. I'm going to increase the propellant a little bit, just to give us enough velocity. So we are going down in our altitude. There's the Florida coast. On the other side of the coast is our runway. Releasing landing gear. Alright, aero brakes. Let's decrease our velocity a little bit. Align towards the runway. Touchdown. Alright, so we have just landed. We have launched from Cape Canaveral. We have delivered a 70-ton payload to Earth orbit, and we have landed safely. And in the future, we hope that ASTRET will get built. That way, what you have seen today will become a reality.
So thank you for taking this journey with us throughout this past year, and this is what we have concluded our project to be.
Thank you very much.